Okay, picture this. You're just chilling at home and then boom, everything goes dark. The lights go out, the TV screen dies, that quiet hum from the fridge just stops. It's in that moment, right, that you really feel how much we rely on this invisible force that powers pretty much everything. So today, let's pull back the curtain and take a look at the simple, elegant physics behind something as basic as a light switch. You know, this simple question, it's really the core of what we're talking about. Why does a light turn on in the first place? And just as important, what makes it go off? Well, it's not magic, I promise you. It's all about understanding the invisible journey that electricity takes, a journey that has some very specific and, honestly, pretty fascinating rules.
So before we can even follow that journey, we kind of have to know what's doing the traveling, right? At its heart, electricity is just a flow of energy. It's carried by these tiny little charged particles, and it's the invisible workhorse that powers our entire world, from gigantic data centers all the way down to the phone in your hand.
And that's the real puzzle, isn't it? This energy can't just, teleport from a power station into your laptop. It needs a path, a kind of dedicated superhighway to get from point A to point B. So, what does this electrical highway actually look like? How is it even built?
And that brings us to one of the most fundamental ideas in all of physics, the circuit. This is it. This is the complete, unbroken roadway that lets electrical energy flow from its source, do whatever job it needs to do, and then travel all the way back. Let's break down what that really means. So the most important word here is complete. An electric circuit has to be a closed loop. Think about it like a racetrack. For the race cars, which in our case is the electricity, to actually complete a lap and deliver their energy, there can't be any gaps in the track. It has to be a continuous, unbroken path from the start all the way back to the finish line. And building a basic one is actually way simpler than you might think. You only need a few key parts. First, you need a power source, like a battery, that gives the electricity the push it needs. Then you connect wires. Those are the road. After that, you attach something to use the power, like a light bulb. And finally, and this is the most critical part, you have to complete the loop. You have to connect the wire from the bulb all the way back to the battery. Once that loop is complete, bam, the light turns on. And this really shows you the all or nothing deal with the simple circuit. On the right, you've got a closed circuit. See? The path is complete, electricity is flowing, and the bulb is on. But look at the left, that's an open circuit. Even a tiny little break stops the flow entirely. There's no partial credit here. The highway is either open for business or it's completely shut down. So, how do we control this whole thing? Well, with a switch. A simple light switch is basically just a gatekeeper for the circuit. When you flip it on, you're physically closing a little gate inside, which completes the path and lets the electricity flow. And when you flip it off, you're opening that gate, creating a break in the road on purpose. It's how we command the circuit whenever we want.
Okay, so we know electricity needs a path, but can that path be made of just anything? Well, as it turns out, the materials we use are every bit as important as the path itself. Some materials are like a welcoming red carpet for electricity, while others, they're like a brick wall, stopping it dead in its tracks.
Which leads us to the next big question. What if we try to build our circuit with, say, wooden sticks or rubber bands instead of metal wires? Would it still work? The answer is a hard no, and this reveals two totally opposite types of materials in the world of electricity. First up, we've got conductors. You can think of these as electricity's best friends or helpers. Things like copper, aluminum, pretty much all metals, they're fantastic conductors because the tiny electrons inside them are free to move around. They put up almost no fight, just letting that electrical current flow right on through. And you can see this perfectly with a little experiment. If you create a small gap in your circuit and then stick a metal spoon in that gap, the bulb lights right up. The spoon basically becomes part of the wire, bridging the gap and proving that metal is a very willing helper for electricity. Now, on the complete other end of the spectrum, we have insulators. These are the blockers. Their electrons are held on super tight so they can't move around freely. That makes it almost impossible for electricity to get through them. They're like a permanent roadblock. So, let's go back to our experiment. If we take out the spoon and put a piece of plastic in the gap instead, nothing happens. The bulb stays off. That plastic acts like a dead end, creating an uncrossable break in the circuit and stopping the flow of electricity cold.
So this gives us a nice little cheat sheet for the rules of the road. On one side, you've got your conductors, the helpers, mostly metals. On the other, your insulators, the blockers, things like plastic, rubber, wood, and glass.
This fundamental difference between helpers and blockers is what makes our entire electrical world tick. But it's also what keeps us safe.
So why is this difference so important? I mean, why do we need both of these things? It's not just about making devices turn on, it's about making them work safely. Let's connect all this back to our everyday lives. It sounds a little weird at first, doesn't it? If insulators just block electricity, why would we even use them? The answer is simple, and it's incredibly important. They protect us. Electricity is a powerful force, and if it's not controlled, it can be really dangerous. Insulators are our shield.
And here is where it all clicks into place. Just think about any electrical cord you have lying around. The metal wire on the inside, that's the conductor, the highway doing all the work. But that plastic or rubber coating on the outside, that's the insulator. It keeps all that powerful electricity safely locked inside the wire, so you can pick it up and plug it in without getting a dangerous shock.
So let's do a quick recap. What are the big ideas here? We've learned that electricity needs a complete, closed loop, a circuit, to flow at all. That energy comes from a source, like a battery, which gives it a push. It travels along a path made of conductors, like metal wires, and, crucially, it's all kept safely contained by insulators, like plastic, which stop the flow where we need them to. It's a simple and, honestly, a really elegant system.
And that really brings us to a final thought. Now that we understand the basic rules of the road for electricity, it kind of makes you think, doesn't it? Knowing how this fundamental force of nature actually works, that's step one. The next step is thinking about how we can keep using this incredible power responsibly to build an even safer and smarter world.